Yeah, hello everybody, welcome back to the course on optical properties of nanomaterials. Today will be the last lecture where we focus on dielectric particles or the optical properties of dielectric particles. And I want to very briefly introduce me theory, you'll see in a second what it is, and then we want to talk about applications of such dielectric particles. Before we do this, I want to briefly recap what we did last week, but start first with what we want to learn in this lecture. So we will talk about the limitations of the Rayleigh theory that we discussed in the last hours of the lecture, and then you will see that the me theory provides a more general framework to describe the scattering properties of arbitrary objects, and this allows us to then evaluate the scattering of differently sized particles, and we will see that there's very strong dependencies on particle size. And then in the second part of the lecture, I just want to discuss with you a little bit on what we can do with these particles. So what were the fundamental insights that we derived in the last lectures? All boil down to this expression of Rayleigh theory. So first we just derived it for very small point dipoles, and then we plugged in material properties via this electrostatic approximation of an electric field. And then we saw, or we derived this equation for Rayleigh scattering. Importantly, again, we see this dependence on lambda, which is the wavelength of the incoming light, as the power of 1 over the scattering efficiency goes with 1 lambda to the power of -4. This is the key trademark, if you want, fingerprint of Rayleigh scattering. And we saw that now we also got an expression for the size of the particles. This goes with r to the power of 6, so a very strong size dependence. But mind you, still in the limit of electrostatic approximation. So the particles still need to be smaller than the wavelength of light in order to be described by this theory. And we also got an expression for the refractive index. And you see that the refractive index of particle, epsilon1, and of medium, epsilon2, are important, and clearly important is the difference between these two refractive indices. And this is something I want to discuss with you a little bit at the end of the lecture when we talk about applications of different scattering materials. What I just want to very briefly demonstrate is this effect of particle size or of radius. And in order to do this, I brought two different particle dispersions that still obey or approximately obey Rayleigh theory. This is silica particles with a size of 200 to 300 nanometers, and this is silica particles with a size of 20 to 30 nanometers. So this one is 10 times larger than this one. The solid content here is 40% and here approximately 5%. So this is much less concentrated than this one. Now I will fill 2 beakers with water. And then move over, and then use these pipettes to fill in we make a dark background, so it should be easier to see. So now you see this, these are the small particles. I think you can see me. Is that correct, Eric? Those are the ones that we had last week. And you see I'm adding it dropwise. If I stir a little bit, not too much is happening. And I keep adding and adding and adding. And if I add quite a lot, so almost a full pipette, you may see a little bit of a blue hint, but it's still fairly transparent. Now I do the same trick with the slightly larger particles. And I fill in approximately the same amount of liquid, but as I said, these are much less concentrated. Oops. Now I fill them in as well. And you already start to see these almost kind of cloud-like or explosion-like patterns. Each droplet creates a much more distinct visual impression. Now if I start to mix, you already see it's very white. And I only added a little bit. If I keep adding more and more, you see it will become, it almost looks like milk already. So this contains much more mass of silica compared to this one, and yet I think it's very clear the difference between these two. Okay, so indeed, there is a very strong size dependence, as we would predict from this r to the power of 6. But still, we cannot really describe larger particles where the electrostatic approximation fails. So what I want to introduce to you now is a way on how we get particle shape, larger particle size. And for this, there is no way, no shortcuts. What we need to do is find solution to Maxwell's equation. So now you would need to sit down, take a pen and paper, and start finding expressions that fulfill Maxwell's equations, plug in different refractive indices of particle material, of surrounding medium, and so on and so forth, and then try to come up with a framework that can solve this. And luckily, this guy here, Gustav Mie, did exactly this a bit more than 100 years ago. So what he did is he found a solution of Maxwell's equation applied to this scattering problem. And his theory, known as Mie theory, can now be used to describe the scattering profile as a function of the angles, so where you sit with respect to the incoming light beam, as a function of the wavelength, of course, and as a function of how the oscillations are. You'll see this in a second. So the problem is there is no general analytic expression except for spheres, no? Because spheres have the most kind of easy to handle geometry. This is what Gustav Mie did. And otherwise, what you need is a computer that crunches the numbers numerically. That's of course also possible, but it also shouldn't be subject of this course. Also, Mie theory, of course, is typically treated by computer programs. That's also not something I want to go into details with. And I just want to give you a very, very basic and very kind of quick run through how this Mie theory works, what needs to be done. And then I just rather want to discuss what comes out of the theory, or in terms of size-dependent properties. Good, okay, so what do we need to do? Mie theory now defines the scattering problem in spherical coordinates that we see here. So instead of x, y, z coordinate systems, you create a coordinate system that specifies a location via two angles, kind of this angle here and this angle, and a distance to the origin. And then the wave functions here are not expressed by a cosine or a sine term or a complex exponential function as we have done it to this point, but by a serial expansion of spherical harmonics. So it's just simply a different way of describing this wave that comes into the material and out of the material. And then you need to tuck in boundary conditions, and these boundary conditions introduce the material parameters. It's exactly the same as what we did last time. No, we say that the electric field needs to be continuous, and the electric field lines need to match at the boundary of the particles. And these conditions then you can calculate the potentials and so on. This is where epsilon1, refractive index of the particle here, or to be precise, dielectric function of the particle, and the dielectric function of the environment come into play. Okay, so what you do then is you define the scattering geometry. Again, you see this spherical coordinate system, these two angles. Then you have an incoming light wave coming from a certain direction, and then you can select the electric field that comes in and that goes out as being parallel to the incoming light field or perpendicular. And this then gives you a scattering plane, and now you can vary these angles to get the full kind, if you want, spatial distribution of the electric light fields, and you always compute the parallel and the perpendicular contribution to the scattering problem. Okay, so now what Mie theory does is compute the components of the electric field, as I said, and this is done via the so-called scattering matrix. And this is where the material parameters, so diameter, refractive index, angles, and so on, that are needed to plug into the equations come into play. So this is really where the boundary conditions that we discussed last week are encoded in these S1 to S4. And here you see what's going on. We have like this matrix here that gives the scattered electric field as a parallel and perpendicular contribution. We have the spherical harmonic, so this is the wave function here. And these matrices here then define the material parameters and the incoming electric field. Okay, so now what the computer calculates is the following. So you get the electric fields, again, as a series of vector spherical harmonics. So you get different conditions or different resonances of the particles that are encoded in these vector spherical harmonics that tell you how the electric field looks like that comes out of the particles upon this scattering event. Okay, this all looks terribly complicated. It's something that a computer typically solves. Before going into detail, what I just said is if we get these different expansions of these vector spherical harmonics, so we get different resonance structures, we would expect to at least see traces of the Rayleigh scattering, because of course this is also a wave that comes out of this. And we will now pay attention to how this will look like, if we can identify familiar patterns that we know from Rayleigh scattering. Okay, what comes out of the computation now is the incident electric field. So this is how you express the wave that comes in. The internal electric field, that's for us now not super important. More important is the electric field of the scattered wave. Now again, this is a sum of all these different modes that come out, or different shapes of the light wave that is scattered out. And you see it always, it's a sum over kind of different components of parallel and perpendicular contribution of the electric field. And you have these parameters here, A and B, and these coefficients, and these actually specify the wave and the size. So see in this A here, for example, is encoded functions to describe the wave, and these are functions of x, and x is a size parameter. So you see x has a contribution of the radius here, and of lambda, which is the wavelength that you use. Okay, and now if we let the computer run these, what you get as a result are, first of all, electric field distributions. So you can look at the central particle, which is in here, and now you can see how the scattered light waves propagate into space. Because the Me theory can give you the intensity of the electric field in all spatial directions and all whatever contributions. And what you see is now, for different modes of these light waves, you get very different patterns here. Now that's what you see here, and you see the higher the mode, the more kind of nodes you have. That's very typical if you get higher harmonics. But most importantly is at the fundamental mode, see 1 and 1, you very clearly recover the shape of a dipole antenna. So indeed, with Me theory, you reproduce at the most fundamental mode this dipolar resonance that we know from Rayleigh scattering. Now the difference is that this is not the only thing that comes out of these equations. You get additional modes that can become stronger and stronger the larger the particle is. Okay, now what you can do, in the beginning it took a long time to calculate this. Now, because computers are powerful, you can, for example, go here, plug in different equations, and then you get the profile. This is the scattering intensity over the angle for a lot of different structures, however you want to specify them. So you can really calculate within seconds the scattering of any sphere or any object that you like. Okay, so take this time. If you want to make a break, go to this webpage and look at it. What I want to do is discuss some very fundamental insights of the theory. So what we do is we vary this parameter x that encodes the size of the particles in a way that we cover radii starting at 20 nanometers to 4 micrometers. And what we would expect is that we find for small sizes, especially here, we should recover Rayleigh scattering, because the particles are clearly small enough that they will obey Rayleigh scattering. And we should also expect that something will change for these values here. Otherwise, I wouldn't go through all these efforts to tell you about it. Then I could just say, Rayleigh scattering works, done. Good, okay. So here's the size parameter again. This is computed for a wavelength of 600 nanometer approximately, 633. silica particles, so you need the refractive index of silica particles, and then you get the parallel and perpendicular components. So depending on whether you look along the electric field lines or perpendicular to the incoming electric field. Okay, so what we see here now, this is the first calculation for a size of 20 nanometers. And what you see is the two components, one parallel and one perpendicular to the electric field. So this should be circles, but they are now cut in half now to save space. And we're looking at two different planes. And what we see here, I'm not sure if you can recognize it. Just look at it a little bit, maybe a bit more. If we look in one direction, you see these two nodes. And if you look in the other direction, you see a circle. And this is exactly the donut that we discussed before. So we have our particle, our dipole particle here. We come in with an electromagnetic wave that travels in this direction, and the field is now pointing in the plane of the blackboard. So we excite a dipole here, and this dipole now, as the field changes its orientation periodically, this dipole moves back and forth as well, and now radiates light waves in this direction. So if we define this as z, x, and y, then we get the following scattering profile. In the plane of the dipole, so z and x, so I'm looking kind of along here, or actually here. Here's the particle again. No, this is where the dipole is excited. I get a distribution that looks like this. This is, if you want, the cross-section of the dipole. And if I look perpendicular to the entire thing, so if I cut the section in here, then I will not see any shape of the donut. So this is kind of the belly of the donut, y and x. And this will simply look like a circle. Now this is when I cut the donut in here. Okay, and this is exactly what we recover from me theory for this one here. So very clear, again, sign of the donut here, and in this other plane, you get a circular cross-section. That's the first thing to pay attention to. Perfectly symmetric, donut shape, and also I want you to look at these numbers. Now this is a relative intensity or scattered light intensity with respect to the incoming electric field, and this is logarithmically presented here, and it goes up to 10 to the power of -8. So not a lot of scattering going on. Next, now x becomes larger, and this x value represents 200 nanometer radius for the particles. So this is approximately what we had in here for this much more scattering silica particles. And now what we see, still there is a donut. Now you clearly see these two wings here in this representation, and perpendicular to the donut axis you get a full circle. But you start to see a slight distortion. So the wave comes from here. Here's the scattering object, and there's a little bit more scattering in the forward direction, along the direction of the wave. But still very closely represented by the donut, meaning that this size still approximately fulfills the condition for Rayleigh scattering. And what you now see is that suddenly the scattering efficiency becomes more efficient. This used to be 10 to the -8, now it's 10 to the -2 or 10 to the -1. So much more efficient scattering, as we already saw in our quick demonstration experiment. Okay, now, so you see Rayleigh scattering, as long as the radius is smaller or the diameter is smaller than the wavelength, is fulfilled or recovered by me theory. Now, hang on, the conclusion, maybe first the experiment. This now is a me profile for an x equals 10, which means a particle radius of 2 micrometers. So again, much larger particle, and now look what happened. It's completely different. You see, instead of this donut shape, now you have a very weird and complex distribution of light in all different angles. So no preferential scattering along kind of the belly of the donut, and no lack of scattering along the axis of the dipole. But now you see you get scattering in all spatial directions, and you get these very defined angular features in here that were not there before. And this comes from a more efficient excitation of more complex modes. Now, if I go back to these modes that we can excite, you see now if you excite such resonance modes, they will distribute light much more differently into space compared to this mode here. Now, here you still see the donut. You see that in plane you have these two wings, and here you see this becomes much more kind of rugged and creates these oscillations that you can also see here. Now, this is encoded in this one here, these different oscillations. And mind you again, the scattering efficiency became more and more as well. Now 10 to the power of 0 is here, now you get much more. And if I increase even further, you see that the whole profile tilts even more, so you tend to get more scattering along the direction of the wave, so in forward direction, and a much more complicated scattering pattern. So what can we deduce from that or summarize from this? No, maybe it's a little bit too dark. First, much stronger scattering with increasing size. Secondly, much stronger angular dependencies. And thirdly, more increase in forward scattering. This is as much as I would like to discuss Mie theory with you. As I said, of course, this is more an introductory lecture, and to get into more details of Mie theory and use computers, you would need to apply a more specialized lecture. Okay, but instead what I would rather do is discuss some applications of dielectric particles. And I just want to walk you through a couple of different kind of aspects where one can use this. And what I want to start with is frosted glass. So frosted glass, where do you need frosted glass? This is maybe the easiest. Typically something you find in bathroom windows because you do not want to be watched while you go to the toilet or take a shower. And what I would also like to discuss with you, how this works and what happens when you add water onto frosted glass, and maybe why. And in order to do this, I also prepared a little experiment. So for this, I first need to clean up. So this is just water now. And what I have here is a piece of glassware from the lab, and you see this is the frosted glass part, and here you have just normal glass. And what I will do is I'll immerse this in water. So this will answer the third question. What happens when you add water to frosted glass? Okay, I think you can see this now, and if I put it in and put it back out again, I think you see that it lost a lot of its contrast. Now it's almost transparent, and before it was much whiter. So clearly, by changing air to water, you change the optical appearance of this piece of glassware. So what is going on here? So frosted glass is done by making normal glass rough. And what you do when you make it rough is, instead of having a plain glass surface, you have a surface that looks like something like this. Okay, so now the surface is rough. You can do this by sandblasting. You can deposit structures on there. Doesn't really matter as long as it's rough. So now these structures here, if they are in the micron scale, they start to scatter light, micron or nano scale. So all of these will now, an incoming light wave that comes maybe from here, will now be scattered in all spatial directions. So as a result, maybe if I draw it here, for normal glass, a light beam that comes from here just goes straight through, nothing else happens. So you don't lose a lot of intensity of the light, and you don't change the angle. This is why normal glass is transparent. If you now have your your roughened glass here, the incoming light wave, now is scattered. That means it doesn't change its frequency or its wavelength. It's just redistributed in space. Now it's redistributed here, 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 and here. So the overall intensity doesn't necessarily need to change. If you sum up everything that comes out here, it may be the same as the incoming light wave. That's typically beneficial because you still want to have light in your bathroom. The only thing you don't want is a straight path of viewing. So here, because you change all the angles, it will macroscopically appear white. Now if I look from here, I will get white light into my eyes, but if I'm looking from here, I don't get the light beam in my eyes. So here it will look transparent to me, here it will look white to me. Okay, another example where you need a frosted glass is when you want to have ambient light conditions. Now, instead of looking directly into a light source, very often, if you look now at the light bulb in your living room, you will see it has a white appearance, and it's the same thing. It makes a rough surface so that the light that comes out of the light bulb is uniformly distributed in space, and that makes it much more pleasant to look at. Good, okay, so now what happens if you add water? We remember that the scattering efficiency scales with epsilon 1 minus epsilon 2 squared, divided by epsilon 1 minus 2 epsilon 2 squared. Or in other words, the efficiency or the energy of the scattered light, the cross-section of the scattered light, is proportional to the square of the difference in dielectric function or refractive index between the particle or the scattering object and the outside or the medium. So here now I have glass particles that scatter light surrounded by a medium. So epsilon 1 of the particle is approximately 1.43. Well, hang on. This is n, the refractive index of silica. So epsilon would be the square root of that. And surrounding this, N2 would be in one case air, and if I add water, then it changes to 1.33. And now you see that this difference here becomes much smaller. I mean, the same is true for the epsilon, and that means that you change the efficiency of scattering, or the cross-section here, the scattering, by reducing this contrast. This is why milk glass looks less milky if you put it in water. Okay, next example. What is the ideal white pigment? So what do we put on our walls if we want to paint them white? So in order to do this, or to discuss this, I first want to reiterate an important kind of thought, and that is that normal pigments work by absorption of light. Now, a classical example, if you look at blue jeans, so the color of my jeans, this blue one is indigo, which is an organic dye that you use to color or to dye the fabric of the jeans that makes it look blue. And why does it look blue? Because it absorbs light very broadly in the red part of the spectrum. So if the red part is broadly missing, what is left is just the high energy side, and that is blue. Similarly, if you look at something that is green, then typically, or if you look at something that is red, then typically this is when green is missing. Okay? So how this looks like, if you have these pigments here, they all contain dyes, either organic ones, molecules, or inorganic ones, some whatever materials that have absorption in there because of their electronic structure. And what you do is you look at the reflected light intensity. Some part of the spectrum is missing, so you observe the complementary color. Now the problem is, if you want to make a white pigment or observe white color, then you cannot afford to miss a wavelength, otherwise it will change the color. So a white pigment cannot work by this mechanism. So that means the ideal white pigment necessarily must involve scattering. So you cannot work with absorption with normal pigments, but you need to work with scattering, or the redistribution of the white light that comes onto your wall into space. This will create a white impression. So now the question, this is what you see here. White pigment works on scattering. And of course, we have a lot of white pigments, right? Think about Abbey Road, think about your own living room. There's a lot of white. So the question is, how do you do this? What do you need to consider to make a good white pigment? So now again, we go back to our formula. And in this case, I just use the formula of Rayleigh scattering because it's a bit more instructive. But of course, you can also solve this for Mie scattering. And we already saw that there's huge differences between different particle size. And this is again encoded here. So you have this option to change the particle size. But you also have the option to play around with the refractive index or the dielectric function of your particle. So to optimize Rayleigh scattering or scattering for an ideal white pigment, so you want to maximize the scattering, and typically you also may want to consider the price of the material that you plug in. So the solution is you make the particles large, because this increases the scattering, and then you make the contrast here as big as possible, and this is by making epsilon 1 high. Epsilon 1 is related to the refractive index of the material. So now you Google, open Wikipedia, and look for materials that have a high refractive index. So we just saw, this is kind of a selection of refractive index. We just saw silica, 1.48. I just used 1.43 here, doesn't really matter, 1.4-ish. Well, not so high. Polystyrene, 1.6, a little bit higher. So this could be an option. But then you see diamond has a very high refractive index. So a very good idea to create a very good white wall would be to grind diamonds into small pieces and then put them on the wall. But of course, this is maybe not very feasible, especially on large scales. So you continue to look, and then you find titania has a very high refractive index as well, 2.6. And this is exactly what streets and wall paints and so on are very typically made of. Okay, now this leaves the question on what is the ideal diameter of this pigment. I already said, no, the larger the better, this is true, but this only holds true for Rayleigh scattering. So if you want to increase more and more, and we've seen at the 4 examples that making them larger and larger actually increases the total scattering efficiency. And now what you need to do is compute via Mie theory the scattering profile you see here as a function of wavelength and as a function of reflected light intensity. And this graph here is a little bit busy. You see this is the visible range. This is what interests us. Now we don't really care if our wall is good at reflecting IR light or other light wavelength. We just want to make it look white. And we see now if you change the size of the particles, this is approximately 100 nanometer. You see already in the visible range, the efficiency of scattering decreases. So this will look a little bit bluish because it scatters blue light more efficiently. Then you increase the size a little bit more, and then you see this one here has a very high scattering cross-section in the visible range. And as you increase the size more and more, you see you extend the scattering much more to the infrared, but the scattering at visible wavelength is a little bit decreased. So that means that you can extract from this an ideal scattering efficiency for visible light, and this has a function of something like this. So the total scattering may be better, but for the visible range you can identify an optimal pigment size, around about a few 100 nanometers or so. And this is how you select materials for wall paints and so on. Okay, next examples, sunscreen. So sunscreen, of course, has a little bit different criteria. Of course, you want to have a high absorption of UV light. That's the whole purpose of sunscreen in itself. So for this, you need semiconducting particles. We will discuss this a little bit later because they are able to absorb UV light. That's not something a dielectric particle like silica or so can do, or they only scatter light. But then again, what you actually don't want is a lot of scattering of visible light. So it's a very different design criteria. And why don't you want to do this? Because typically, if you want to go to the swimming pool or sit in the garden and read a book, you don't necessarily want to look like a geisha. So here you see, this is an example where the scattering at visible range is optimized. Now this would make you look very, very white in the face. But typically, I mean, this may be beautiful, but it's not something you typically want for your personal benefits. So again, you go to the equations that govern the scattering. And now you see that you need to optimize in a different way. Here, you want to reduce the radius of the particles to make the scattering efficiency less and less efficient. And here's an example how this works. So this is titanium dioxide, also a semiconducting material, so it can actually work as a sunscreen. And dispersions of different particle sizes all have the same dispersions, 20% titanium dioxide, and you see the same effect that I showed you earlier with the two silica particle sizes. The smaller the particles, the less light they scatter, and the smallest ones essentially become transparent. Of course, now this is only one part of the coin. You also want to have high UV light absorption efficiencies, and there must be a balance of these two things. So here are some simple calculations that Robin Taylor gave me, and you see extinction, so scattering, and absorption for different particle sizes, in this case of zinc dioxide particles that are typically in sunscreen. And you see that with increasing particle size, so from black to blue, all of these parameters increase. But you also see that the scattering, which you actually don't want, is very strong for these large particles here and also here in the visible range. So from here to here, you also have for the 150 nanometer particles already a lot of scattering. While for the smaller particles, you get this more continuous decrease, and the absorption here at UV light exceeds the scattering. So you see still, of course, the absorption is also overall better for the larger particles, but comes at a price. But now, if it now starts to get warmer and warmer, and you go to a supermarket or what and buy sunscreen, and if you buy something with a factor of 10 and something with a factor of 50, and you put it in your face, you will very clearly see that the larger this protection factor is, the more white you will look like. And this is because at the end of the day, if you want to have a high protection, you cannot avoid scattering completely because you need to move in this direction. So this is why then the sunscreens will look more white than these lower factor ones. Okay, so two more kind of things or fun facts. How can we optimize the white pigment? So now we know how that we can play around with the refractive index, and titania is a very good solution if you don't want to use diamonds, and this makes a lot of scattering. But here is a story that comes from a white beetle in nature. And nature, as good as it is to create structures, is not super efficient at creating different materials. Now we as mankind have, of course, all these different technologies to dig things out of the earth and change them, so we can make a lot of different materials, metals and metal oxides and you name it. Nature is not so good. It needs to work with what it has, and what it has is typically organic materials that you can produce by metabolism. Yet, nature achieves very stunning color effects. And here's a story how they call it eerily white beetle influences a super white material. And what the authors say in this article here, if you're painting a wall white, you have to paint a few times. I think this is something that everybody knows. No, and that is highly annoying. So from the University of Cambridge, Olympia says the material that they developed can paint a wall with a 10 micrometer thickness. So that's smaller than the width of the finest hair. It's true, like a typical hair is 50 micrometers in diameter, so you can make a very thin layer of paint and your wall will look beautifully white. That's a good development. So how does this work? This is the eerily white beetle. No, Lepidiota stigma. I'm not a biologist, but you very clearly see this is a white beetle. And now if you take a look at the structure of this white material, then it looks very strange. No, it's a very thin material. There's a lot of kind of distances between it, and it has very anisotropic structures. And you see the reflection is fairly high across the entire wavelength range. So this makes it look white, otherwise it would look colorful. And now what these researchers did, this is the group of Silvia Vignolini in Cambridge. They looked at the structures and now try to find a synthetic material to reproduce this. And what they used is cellulose nanofibers, which is actually something that is very biocompatible. You can eat it, and this comes from paper. So it's very simple technology. You don't need any titanium dioxide, any complex fabrication methods. This is one of the simplest materials you can imagine in terms of fabrication. And now what they looked at carefully is how the distribution of these cellulose nanofiber diameters and thicknesses and length looks like. Now this is what comes out when you extract this or when you buy it. And now they started to centrifuge and dilute. Now first they get rid of the very small ones, then they redilute this, then they get rid of the little bit larger ones, and then they leave these coarse fibrils. And you already see, because now the diameter of these becomes larger and larger, they also scatter more efficiently. And you see this clearly here at these two pictures. Again, somewhat similar to the experiments that I did. These ones scatter more light, so they look whiter. Now if you paint a paint from this, you see here, this is this dispersion, this one is this dispersion, and this one is this dispersion. And you see that you can paint this over very efficiently, and you hardly see any underlying structure anymore. And in the SEM, so the electron microscope, if you look at this coating, you clearly see the difference. All images have the same scale bar, and here you see these very big chunks that are still surrounded by smaller chunks. And this seems to be very efficient at overall scattering the light in all directions, so that to make it look as white as possible with the minimum amount of material possible. And the explanation why this is so good, both in the beetle and in the structure, is first you have large scatterers, and they are anisotropic, so by nature they have a very high tendency to scatter light. Then it's polydispersed in nature, so you can get a very kind of disordered and uniform structure in space. And because of this polydispersed nature, you increase the path of light within the material. So because of these large free spaces, light is very efficiently distributed within the film and then scatters more and more in all directions. And that means that it's more and more distributed and comes out whiter and whiter. Okay, last example. What people do kind of in, if you want, cutting edge research. We know from microscopy that the resolution of a microscope is limited by Abbe's limit, and you cannot see structures that are smaller than approximately, let's say, a few hundred nanometers or so, because you cannot resolve them anymore. And now researchers here in Erlangen at the Max Planck Institute for the Science of Light, this is the group of Wahid Sandoktar, they developed a method that uses scattering to make the resolution of a microscope larger. And what they do is, you see it's a fairly complicated setup, but they look at an object here, and I will just show you that they, for example, use individual proteins with a size of less than 10 nanometers or so much, much smaller than would be normally possible to see. And what they exploit is the scattered light that comes from this object and the interference of this light with the incoming light beam. And then they do a couple of steps, and then they can detect it by a camera and can then back calculate actually or see individual scattering objects. And what you see here is proteins that are secreted by a cell. So this is, I think, a cancer cell, and they focus their light next to the cell because they actually do not want to observe the cell. Any microscope can do this, but they want to know how many proteins and which proteins come out of the cell. And of course, this can be very relevant because from this you can learn how a cell changes the exprimation of proteins according to different stimuli, whether a cell is sick or not, and so on and so forth. Now maybe what changes when a second cell comes, and so on. And here you see, here and here, very clearly the contrast given by individual proteins. So extremely small objects with an extremely weak scattering cross-section can still, if you play the game cleverly, can still be made visible in a microscope. And with this, I want to end the lectures on scattering by briefly summarizing that me theory describes the scattering of larger particles, that the larger the particles get, the more it becomes angle dependence and kind of size dependence. And then I gave you a lot of different examples where scattering is used both in daily life and in modern technology. And what you've seen, I think, in all these examples, that you need to adjust product properties via the material choice, the particle size, and as you've seen for the super white beetle, also by the arrangement of these different building blocks or contributing building blocks in space. From this on, we will now move to different material systems. In the next week, we will discuss metal nanoparticles. And until then, I wish you a good time and see you next week. Goodbye.